I can start now? Yeah. Okay. Yeah, good morning everyone. So, welcome to this lecture series here. Uh, so, I'll be talking about a subject called astronomical spectroscopy. I'm sure that most of you already know what spectroscopy is and what astronomy is to a very basic level. And during the talk, I will be sticking to the very basic of these two subjects, how the spectroscopy is combined and used in the astronomical application. To start with, if you look at the very basic spectroscopy, which I'm sure most of you already know that the spectroscopy is technique of separating photons of different energy or wavelength from a broadband electromagnetic signal. Or in simple words, you say that it is seeing colors. And what is shown here is a prism which is dispersing light. So if you are getting white light, which is a broadband signal, when it passes through the prism, it gets dispersed, which means that the light is divided into its primary colors, and then it emerges out, and then you see the photon spectrum. I'm sure most of you have already encountered this, have already seen these experiments in your laboratories. A very fascinating thing that we humans and some other mammals have also got an ability to see the colors. And eyes basically work as a natural spectrograph. As we know biologically that eyes have photoreceptor cells. It has rods and cones. Rods are basically insensitive to colors and help seeing objects in low light. Cones have photopigments which are sensitive to colors and they get stimulated in brighter light. It is estimated that humans can distinguish up to 10 million colors, about 6 million cones and about 100 million rods help in perceiving our vision. And so it's very fascinating that we as humans are equipped with the natural spectrograph and we use it in everyday life to visualize color, to perceive color, and to enjoy this basically beautiful world. If we go, I guess you have to move out. So the scientific application of spectroscopy started, and it appears that the astronomical objects motivated scientists to pursue spectroscopy for scientific explanation. And this is the famous picture or the drawing how in 17th century Newton made an experiment on sunlight to cause a spectrum. So this is basically the sunlight coming from a pinhole, and he used a prism-like device and he could see the spectrum. And there's a very famous quote which is very relevant. And he said that if the sun's light consisted of but one sort of rays, there would be but one color in the whole world. And that basically, we know it very well now, that we see colors because sunlight has colors. In fact, since eyes have a very good ability to resolve colors, it's not very surprising that all ancient civilization, including the Indian civilization, had realized colors in astronomical objects as well as in everyday life. And it appears that in the ancient texts there is a description of some kind of colors of astronomical objects. In fact, there is a description of some kind of spectrometer also, and this is what is presented here. So this is basically in Sanskrit and all that, where people have tried to decode it, and it's a very simply, it's sort of indicating that there is a description of spatial dispersion as well as how many colors one could see from that instrument. And I'm sure that most other civilizations have also seen or realized the spectrum, natural spectrum in one or other form. Going back to the modern science, we have seen the work of Fraunhofer, Kirchhoff, and Bunsen. And if you are a chemistry student, I'm sure you know these names very well, including the physics students. But they got most application in the chemistry, and that's because what Fraunhofer saw in the sun's spectrum, that apart from this famous rainbow, which is like what you call the violet, indigo, blue, green, yellow, and red, he also saw the dark bands within the spectrum. And these dark bands are known as Fraunhofer absorption lines now. It was a mystery at that time that what causes these absorption lines in the sun's spectrum. And this was basically understood later on by the full team, which consists of Fraunhofer, Kirchhoff, and Bunsen. And the Bunsen experiment is very famous. What he did, he created a flame, which of course has a very high temperature. And he dispersed the spectrum of this flame, and he saw that apart from the continuous spectrum, there are spectral lines. And when he put that flame in front of a bright, a hotter source, what he noticed is that when he was seeing the emission lines, when there was no background source, and when he put the background source, he saw at the same location absorption lines. These absorption lines match with the elements present in the basically the flame or the smoke which is coming out. So there are many hydrocarbon elements and all that. And so he realized that the spectrum actually carries the signature of elements. They will appear in emission if heated to high temperature, but they can appear in absorption if seen against high temperature background. And that gave a very fundamental explanation for the absorption lines seen in the sun spectrum. Now it so happens is that sun is one of the very intense source of light, which has all these absorption lines as well as continuum spectrum. So undoubtedly, sun played a very important role in understanding modern spectroscopy, and many experiments were played around basically sun. So if we go to the work of Raman, C.V. Raman and M.N. Saha, there is thing about theory of color. So Raman primarily was interested in explaining the colors in the nature. And now we understand what Raman's theory was, that it basically describes change in wavelength due to inelastic scattering of photons by matter. That technique is basically used in identification of minerals and organic material, and this is one of the spectral signature of benzene, which was published by C.V. Raman. Then there is a famous ionization equation of Saha, which is basically describing the population ratio between successive ionization stages. So if you have various elements, different temperatures, then you can predict what is the ratio in the ionization state with respect to the neutral state or in multiple ionization states. This is used to estimate chemical and physical conditions of stars by analyzing light intensities. And now this has become a very important tool to understand the spectrum of stars. In fact, if I go to this famous slide, where what is shown here is the spectrum of a star. Astronomers divide the spectrum in different types. What is represented here is starting from O type, B type, A type, F, G, and K, M. What differs here is the surface temperature. So O type stars are the hottest, where the temperature could exceed 40,000 to 35,000 Kelvin. If you go to the cold stars, which are like M type, the temperature is smaller. And what was seen in this spectrum is that the stars which appear bluer, which are the hotter stars, have fewer absorption lines, and stars which are redder or which have low temperature, surface temperature, have lots of absorption lines. And this was not really understood. The spectrum was known for many stars, but it was not really understood until Saha published his ionization equation and explained why stars of different colors show different kinds of spectral line. It is not due to different composition, but it is because different states of ionization of elements on stellar surfaces have different temperature. So it is understood as a physical condition and not primarily due to the composition. And that was a breakthrough at that time And that's why Saha's work is very important in spectroscopy. I will not have time to really go into the details of each and every aspect of spectroscopy, how it is used to, get many science aspects of modern astrophysics. But in summary, the spectroscopy is a tool to study presence of elemental abundances in stars, in galaxies, in interstellar medium. Interstellar medium is basically medium between stars. So medium between stars is not empty. It has a lot of gases, lot of dust. It has a lot of interstellar chemistry, and that all is derived from the spectroscopy. All these spectral lines together fetch information on temperature and density of medium in objects. Through Doppler effect, which I'm sure most of you already know, that when an object is moving and emitting certain frequency, the frequency which we receive is different from the frequency it was emitting, and that shift in the frequency is related to the velocity with which it is moving. And so the Doppler effect can derive the velocity information, and that is done by looking at the shift in particular spectral lines, and that can be used to get distances to the object, because in astronomy the velocities are basically linked to the distances. When there are tiny changes in Doppler velocity, they can be used to search and find planets around different stars. In fact, that's one of the techniques which is used to search for planets, and that's a spectroscopy. So spectroscopy drives the search for planets around distant stars. Another effect which is there in the spectroscopy is called Zeeman effect, which is the hyperfine splitting of lines in presence of magnetic field. So in fact, if you see a particular line is split, you can derive a magnetic field. So interesting thing about astrophysics is that, and this is also the fascinating, that we do not have access to these objects. We are not in a laboratory kind of environment. What we receive from stars or distant stars or galaxies is only the light, or the photons. And these photons needs to be analyzed, and by analyzing these photons, you can get information about temperature, you can get information about density, you can get information about its kinematics or its dynamics through Doppler effect. You can also get information about magnetic field. And so you can understand that these feeble photons which are coming from so distance, we analyze them in telescope, we use different techniques like spectroscopy to derive almost everything about them. Okay, and so that's very important to realize. Now I will go ahead with the next slide, and I will be putting some time for spectroscopic techniques. So if you look at the spectroscopy, how spectroscopy is done in astronomical context. So I will take examples of three major wavelengths: radio astronomy, the radio wavelengths, which are meter to centimeter wavelengths; then optical astronomy, where it is submicron to micrometer wavelength. And in fact, the pictures what I am showing is the giant meter wave radio telescope in Pune, which is one of the largest telescope in the world, or largest radio telescope in the world in terms of collecting area. Then we have 3.6 meter Devasthal optical telescope, which works in the optical, basically visible as well as the near infrared region, which is at Nainital. This is the largest in India. And then we also have an X-ray payload, which is AstroSat, which was flown in space by ISRO a few years ago, and that is an X-ray thing. Now, all these branches of astronomy, or all these wavelengths, basically do spectroscopy, and I will briefly go through each of them. So first we start with the low energy or the higher wavelength, which is a radio telescope system. So a radio telescope basically receives naturally produced radio emission from celestial objects. So there are many celestial objects which are naturally emitting radio waves at different frequencies. So you receive them through a large dish antenna. This is basically the collecting. You amplify the signal which is received, and then you process it. So process is basically electronically processing, and that is done in a device called correlator. So what we actually do to process this signal which is coming from radio antennas, we use the technique of Fourier transform. Now, Fourier transform or the Fourier series, which is a mathematical subject, and I'm sure most of you have gone through that. The Fourier transform has got a very wide application, not just in mathematics to understand it, but it has got very high applications in every branch of physics, every branch of chemistry, as well as in other branches of signal processing. And what basically you do, if you have a time series, a signal which is represented as a time series, you can Fourier transform it and convert this to frequency domain. And so the frequency component can be realized there. And radio engineers exploit this in correlator. Just to recapitulate what you have been studying in your classes about Fourier transform is that if you have certain things in time domain, you can convert them to frequency domain. So for example, the first one is being shown here as a delta function. If you do Fourier transform of delta function in the frequency domain, this becomes like a consists of many frequencies, almost all the frequencies. So thing to remember is that a signal which is narrow in time domain is wider in the frequency domain. If you look at the boxcar function, if you do Fourier transform, it forms a sinc function. If you have a sine wave, which basically has single frequency, you get the frequency spectrum which shows single frequency. If you have multiple frequencies here, it will show those many frequencies. So for example, it is shown here as a Coombe function, which has a set of frequencies, it has got similar set of frequency components. So that is how you do spectroscopy in Fourier domain. In fact, to simplify this concept, if you first look at what I'm showing here on the right hand side, and you know that if you look at the Fourier series, you can represent a time varying signal as a sum of cosine and sine components, which are basically monochromatic components. So for each frequency, you can derive that. So basically, the Fourier series, what it does, every time series is converted into a set of frequencies, okay? And that is what is the spectroscopy in a very general sense. And in fact, this technique is used in many laboratory spectrometer, and that is why I put it here, because I think some of you might have worked on such spectrometers in your advanced physics or chemistry lab to analyze the composition of elements, and which is a representation of also the Michelson interferometer, where you have two mirrors, and if you move the mirror, by moving the mirror, you change the path difference, and so the light which is coming out through the constructive and destructive interference corresponds to a monochromatic wavelength. So as you change the distance, this wavelength changes, and that's how you form this spectrum. Another application of Fourier transform you see in your daily life is in many of these music applications which you come across in your laptops or in your mobile phones, where you can tweak in what you want to hear and what you don't want to hear. So this is also a time varying signal, and you can Fourier transform and get a power spectrum. This is an example for a human voice spectrum. And then you can tweak in whatever. You can lower some part, you can increase some part, and that is also basically the Fourier transform. Now, to realize a Fourier spectrometer electronically, such as in a radio telescope, there can be two ways one can think of. One is to create very finely divided filters. So if you want 1,000 frequencies, you can devise 1,000 filters. But that's not a very good technique, because each time you take a measurement with a filter, other filters are, a light from other filters is lost. So it's basically not a very good way to do that, because it's a light loss mechanism, and it's also very cumbersome. You have to design different filters. And there are now more intelligent ways, basically by using the digital signal processing. There is a digital filtering and sampling, and then you can attach correlator to each filter for correlation of the signal. So if you are a radio engineer or if you are an electronics engineer, what you have to look at is the correlation function. So if you have a voltage series, which is a time series coming, and they are coming from, let's say, from two different devices. In this case, there could be two different antennas. And if you multiply, you basically correlate them with a time lag. And if these I and j, what I'm representing, come from the same antenna or the same devices, this becomes an autocorrelation function. If it is coming from different devices, it becomes a cross correlation function. And this function is basically giving you information about the spectrum, and that's how we will see how it is done. So for instance, there is a scheme called the FX correlator, which basically means that you first do Fourier transform and then multiply the two signals. So remember that in a telescope, radio telescope like GMRT or other telescope like Very Large Array, you have multiple antennas, and these antennas, the signal is combined. So if you have n antennas, n signals are combined basically. So here I am representing the two signals, two voltage series, basically V as a function of t, and another V as a function of t. You introduce basically delays, do a Fourier transform, which is fast Fourier transform. You do the same for other antenna, signal from other antenna. You bring it together, multiply it, integrate it, and then do the Fourier transform basically. Then you do the integration. So Fourier transform followed by multiplication and integration. This is one of the scheme, and you can solve it mathematically. That when you do a Fourier transform of the signal, it is basically multiplication of the voltage by its response function. And when you do a Fourier transform of two functions which are multiplied, when they come out, they become Fourier transform of one function convolved with the Fourier transform of another function. And so every time you do Fourier transform of the voltage series, you generate a Fourier transform of the voltage, but it's modified or it's convolved by a sinc function. Okay, that's because the response function was a rectangular function in this case, which represents a finite bandwidth in that particular thing. Now when you correlate it, in this case it's a cross correlation because you bring the signal from two different antennas, then you get a visibility function, which is a multiplication of basically the two Fourier transform here, convolved with a sinc square function. So these are the details, mathematical details. So thing is that you are interested in this because Fourier transform of voltage series at the time series will give you frequency spectrum, but you won't get the frequency spectrum directly. This will be modified by a sinc square function. There can be another scheme which is called the XF correlator, where what you do, you first multiply the signal and then do the Fourier transform. So you bring the signal from two different antennas, you create, so for example, one signal is directly coming and another signal, each time you multiply with the second signal, you introduce different time delays. You first multiply, then integrate, and then you do the Fourier transform. Okay? Because these multiplication and Fourier transform is a linear function, you can do either this one first or the other one first. And so the result is same, except that when you do first multiplication and then Fourier transform, you do not generate a sinc square, but you only generate the sinc function because it appears only once, because you have already multiplied and then you did the Fourier transform. So only difference between the first method and this method, FX and XF, is that in both cases you do generate Fourier transform, which is the frequency spectrum, but the convolution function is different. And that makes some, pros and cons about the two methods in radio astronomy. So if you look at the first one, which is XF, and the second one here is the FX. So here it is a sinc function response, here it is a sinc square function response. And these are the channels. Channels basically means every different frequency. And so what you see here is basically you want, let's say in the fourth channel in this case, this kind of theoretical response, which is a good theoretical response is a box score, basically a rectangular function, where the response rises sharply, stays constant and decreases. But in practice you won't get that. That's because there is a sinc function. And so the signal which is in fourth channel, for instance, in this case, will also go into the another channel. So there is a contamination. And the side lobes are at the level of 22% maximum. And that's actually significant. So there is always a spillover to another channel. But when you do FX, you basically get a sinc square. And so these are dampened compared to the sinc, and you get only 5% side lobes. So when basically people work with either FX or XF correlator, you do get these responses, and people remember that the signal which is appearing in one particular channel is also going to other channel, and there are ways to mitigate that, ways to understand this when people explain these spectrum. but we live with basically these shortcomings in all these things. Now, one of the application of the radio, just to realize you how important the spectroscopy is, and I give an example of a very famous line in a spectroscopy and radio domain is the line of atomic hydrogen. You know that hydrogen is the most ubiquitous element in the universe. Everything, stars, the matter between stars as well as in galaxies, hydrogen is there, and hydrogen is the most abundant one. Hydrogen, basically, if you look at the hydrogen atom, that has got in the nucleus a proton and electron, and proton and electron can have same spin or different spin, and that makes a hyperfine structure. So and they can randomly flip. Okay, so when they randomly flip over a long period of time, there is energy difference of about 5.9 microelectron volt between these two states. And when such a flip happens, when electron comes from a higher state to the lower state, this is a magnetic dipole transition, which comes at a frequency of 1420.4057 megahertz. So there is a loss of a screen in front of me. Yes, so I'm back. Okay. Now this transition is a forbidden transition, and this is because, as I said, hydrogen is there in the galaxy, so you can use it to map hydrogen atoms. Okay, so this is H1 map of a galaxy. These are radio contours, and then, as I said, you precisely know the frequency of what this H1 line has, which is 1420.4957 megahertz. Every pixel also has information about its velocity, because when you receive it, this frequency shifts. So depending on whether the object is going away from you or coming towards you, you can get a blue shift or a red shift. Now, of course, most of the objects like galaxies are going away from you, and so you always get a red shift. But within the galaxy, there is a rotation. So part of that can appear going away from you, and part of that can appear as if coming towards you. And so what you see on the right hand side here is the velocity map. So each point in the galaxy can be attributed to the velocity. And that is what I have been telling that in the beginning, that spectroscopy is very important to get the dynamics or the kinematics of galaxy. And this is one of the examples which I wanted to show you. Another aspect of doing radio astronomy, basically radio spectroscopy, is the molecular transition. And I'm sure some of you might have read about this in your classes, is that certain molecules have non-zero dipole moment, and depending on how much dipole moment they have, you can basically get a rotational vibrational transitions of that. So if you plug in this formula, the most common numbers like the mass, the radius, and the dipole moments in energy in the dipole moments, basically when you work it out, the frequency comes about terahertz, which is in the millimeter waves. And so there is a whole terahertz astronomy, which is somewhere in between radio and optical in terms of frequency. So it's neither a low frequency, but it's neither very high frequency like optical. Now we know that hydrogen is the most ubiquitous element, but hydrogen molecule form does not have any dipole moment, because it's a symmetric molecule, so it has no terahertz emission. But wherever there are molecules formed, apart from hydrogen, there are carbon monoxide, ammonia, water, HCl, and all that. They have a strong terahertz emission line because they are a symmetric molecule and they have a non-zero dipole moment. And so these lines can be studied. So just to show you one spectrum here, that is the spectrum towards the Milky Way center. And what you see here is the terahertz lines, and not just one line, you see basically a whole lot of lines there. And they consist of very different kinds of elements, very different kind of molecules formation, many aldehydes, many types of alcohol, many types of long polymer chain. And in fact, that's why there's a whole area in astronomy which is called astrochemistry, which basically studies formation of such complex molecule in this space. These complex molecules are very important for life aspect, because we are made of not simple molecules but very complex organic molecules in us. And so there is always, a quest for understanding that how, the life gets formed, and astronomers look for a connection in the in the space, that you see such molecules, and if you see such molecules, you sort of get a hint of how, life could have been evolved. And these are very crucial for formation of stars, as well as I said, in the biological context. And so the radio astronomy is basically giving you a lot more, information, uh, not just for astronomy, but also for very different areas. Now I will quickly come to the another wavelength region, which is the optical spectroscopy. So I'll talk about optical spectroscopy in spectrograph. Now, I said in the beginning that optical spectroscopy is something which we realize in our everyday life. There are several natural phenomena which we see. For example, the rainbows. We get fascinated by that. And there is also about the colors. So whatever colors we see, whatever we are seeing around us, if this room is yellow, the leaves are green, we know that because there is a white light falling on that. So when you see a leaf as a green, it's because it is absorbing all other colors but leaving out the green color. And therefore, this is perceived as a green light. And so, the visible light is, of course, only a very small part of the spectrum. And before we really go, can we, yeah, it affects my movement, okay? So if you stand still, then I can do a better presentation, okay? Unless you are required to be there, yeah. So the one thing about spectroscopy is the spectral resolution, which is basically the wavelength divided by delta lambda. Delta lambda is the smallest wavelength separation which you can resolve in the spectrum at a particular wavelength lambda. So lambda over delta lambda is basically spectral resolution, and that's one definition I would like you to sort of always remember. And if I go further, yeah, for some reason this is really bad arrangement here. Dispersion by material properties. So we can actually generate the spectrum by different techniques, and one of the techniques is selective absorption. So we know that some glasses can, so for example, like as I said, you look at the colors in the thing. So if a leaf is green, that's because it's absorbing other colors but leaving out the green color. And so there are certain glasses which have been made with impurities pigmented in that they can selectively absorb some colors while letting pass a particular color out. So these glasses pass broadband colors with bandwidths about 100 nanometer or so. So that's why you get sometimes very beautiful glasses, the red glasses, blue glasses, and all that, which we also use in spectroscopy. But this is a form of very low resolution spectroscopy. While if you go to slightly higher resolution, where you can see colors in a very distinct way, is by prism. And the way prisms work is because there is a refractive index. So for example, glass has a refractive index of 1.5. But one thing you have to realize is that the refractive index is a function of wavelength in material. Almost all materials show that. Some materials show it more, some materials show it less. And so different wavelengths respond differently to different, differently in these mediums. So for example, the bending or the refraction which is being caused is different. So that is how the prism disperses light. When the light comes, the bending of different colors, starting from the red to the blue side here, is different. So the red side is deviated less, while the blue side is deviated more. And the geometry of prism makes is that these colors are basically separated out when they come out of the prism. And so you see basically colors from the prism. This is a spectroscopy, but this provides a very low resolution spectroscopy, which means that you possibly cannot resolve many colors. Although colloquially we see it with pure violet, indigo, blue, green, yellow, and red, the 7 colors, but practically you see more than 7 colors there. But it's a very low resolution spectroscopy. If you want to do high resolution spectroscopy, which means that we want to resolve more and more colors, hundreds of colors or thousands of colors or wavelengths basically, we have to go by different techniques, and here we have to employ diffraction gratings. I'm sure most of you have read about diffraction grating. So there's a famous grating equation, which is, you know, that you have the order of the diffraction, which is equal multiplied by lambda is equal to d sine alpha and sine beta, which if you go to any primary elementary optics book, you come across that, where d is the groove spacing. So what you do in the grating is that you make some arrangement that there are grooves formed at certain frequencies. Group density has to match with the wavelength of the light. So for example, if the wavelength in the optical is of the order of micron or submicron, the spacings are also of the order of submicrons and all that. So that there is a diffraction phenomenon. The gratings can be basically work in either in a reflection mode, for example, is shown here, and it is forming like the 0th order, 1st order, and 2nd order, as well as the higher order gratings are there. Or they can work in the transmission mode, where there is a there is a transmitting material, there is a grating engraved on that, and when the light passes through the grating, it forms multiple orders. So one thing is that all light passes through the grating, there is a very little loss of light, but this gets divided into multiple orders. So if you can image only one order, the another order's lights are basically lost. One thing to remember is that higher order and higher group density provide higher resolution. So if you work in higher orders, basically not the 1st, 2nd, 3rd, or even 10th order, or even 50th order, right, the resolution gets multiplied by that. And to get finer and finer resolution, you need to reduce the group density, basically. Okay, so if you want to get high resolution, you have to tweak in either you have to work with higher order, or you have to reduce the group density. Now, in fact, one of the example which you see in everyday life is the colors produced by the DVD, the normal DVD, is because DVD or optical media, they work by the optical light, and their group density is of the order of wavelength of light, so they're nicely diffracted. They are basically a very cheap grating which is available to you. But in astronomy, of course, the gratings are very large and very perfect, close to the perfection. We demand very large size gratings are produced. That's because we need them for large spectrographs. Another way to produce dispersion could be by interference. And in fact, the famous example is again when you look at the soap bubbles, lots of kids do that. You see a lot of these colors, very beautiful color changing thing. And that happens because there are multiple reflection in thin films. And that theory is also there. You form constructive and destructive interference pattern to tune the pass band. And one of that application is done in Fabry-Perot at Lyon. It's possible that some of you have already read about that. So what is happening there? There are two highly polished surfaces, and their orientation is fixed to the submicron accuracy, and you can change the distance between them at very fine distance. And so depending on what is the separation between the two plates, and if you additionally you can put certain material in that to tune it, you can really produce very narrow pass band, sometimes as narrow as less than 0.1 nanometer. And so they are very useful for very specific application if you want to detect certain objects in a very specific line, astrophysical line or any other common line. And so the Fabry-Perot at Lyon are very commonly used in astronomy as well as in other applications, for example in telecommunications and all that, where certain wavelengths are transmitted to the optical fiber, and so you basically make echelons and all that to reduce the noise, for instance. So this has got application in all kinds of technology as well as in astronomy. I'm trying to move my slide. Yeah, so if you look at the astronomy spectrograph, so basically the idea is taken from there. Now you have to put it so that you can do a meaningful observation with a telescope. So this is a very simple form of astronomy spectrograph. What you do is that this is like in the telescope, light coming from the telescope. So this lens is representing the telescope, and then light is converging. You can make a slit, and then you can make a collimator So why do you need collimator is because you need to again make it plane parallel so that the dispersive elements can do uniform dispersion coming from different angles. And then you can basically put another lens to focus the light on the detector. Okay, so this is a very simplistic drawing for any astronomy spectrograph. And what is represented here, for example, the zeroth order and then first order, and so this is first order on one side, there is a negative order on the other side. Similarly, second order will be formed at higher distances and all that. So this is a basic spectrograph design. And because we here in Nainital have India's largest optical telescope, which is a 3.6 meter Devasthal optical telescope, this has got several spectrographs, and one of the spectrograph was designed here and built in ARIES, Nainital. And remember, when the telescope sizes become large, the spectrograph sizes also grow. And these spectrographs which we have, for example, what we call here is the ARIES Devasthal spectrograph, is a bulky spectrograph. It weighs 350 kilograms. You have to sort of be very precise. The optic size is very big, sometimes as big as about more than a feet or so. The whole length of this spectrograph is about 2 meters. So these are really very large spectrograph for that to handle it, to make it. A lot of expertise is required in that. So this is how this spectrograph works. Of course, what I have shown previous slide is a very simplistic diagram, but in reality, the optics produces many distortions, many aberrations, so we need to correct it through the multi-element optics, and that's why a realistic spectrograph is much more complex than simply a lens and a collimator and this thing which you might have seen in your labs. So a spectrograph is basically here used to make a spectrum of very faint stars and galaxies. You just have to go, yes. Can you do it from there? Next slide. Yeah. So another complex spectrograph for Devasthal, which is under construction, this is a collaboration between IUCA and ARIES Nainital, which is based on optical fibers. So optical fibers form flexible slits here. So the slits are formed by the fiber. So light is basically collected from the fiber. So we have multiple objects in the sky which can be observed at a time in a single setup. So what you see here is a very complex setup of spectrograph which we do. So this is depicted here, that if you have a field where there are multiple galaxies or multiple stars where you are interested in, you can place these fiber units and bring it together and do spectroscopy. Because we want to gain speed, we want to cover many objects at a time, the complex spectrographs are basically a necessity, something like what I'm showing here. What you see in this spectrograph is basically, it is recorded on certain detectors, certain electronic devices such as the CCD camera. And this is one of the, because CCD cameras are not really showing you the colors directly, so we need to do many calibration aspects and all that. So for example, this is how a typical spectrum looks like when you record it on a CCD camera. And when you process it, you can basically generate the flux versus wavelength. So this is one example taken from 3.6 meter Devasthal optical telescope, where a supernova spectra is shown. So what you see in these spectra, if you look at first here, which is the raw spectrum, you see these dark bands. Go back to my previous slides. Remember that there are these absorption bands which we are seeing. Okay, so these absorption lines, particularly what you see here, is the Balmer series of hydrogen. You are very well aware of this Lyman-Balmer series. Balmer series comes in the optical design, and you see these Balmer series of hydrogen. When you analyze the spectrum of different elements, you see basically many other species. For example, apart from hydrogen, you see iron, you see sodium, you see calcium, because we know what are their laboratory frequencies. So if I know that the singly ionized calcium or doubly ionized calcium or singly ionized sodium or iron and all that, what are their precise frequencies? And you put it there, and that's how you can identify these lines. So spectroscopy tells you about how many elements are present and how much they are there By studying the line intensity ratios, you can actually get a clue about what is the temperature, what are the excitation mechanism, and so which are related to the temperature intensity. And so spectroscopy, particularly optical spectroscopy, is very useful for studying stars as well as the star forming regions. And when the stars are basically exploding at the end of their life, what they had in their interiors, how much they have processed the material. This all information can be extracted from optical spectroscopy. Just to give you another example, that certain applications in astronomy require to achieve very high resolution, and one of that is achieved by SL spectrograph, SL grating. Some of you might have already read about SL gratings, which are basically work in higher orders. So remember, when we are working in lower orders, like in gratings, transmission gratings, we mostly work with first or second order or maybe third order. But remember, to achieve higher resolution, either you have to reduce the group density, the separation between the groups, or you have to work at very high order, like 50th order, 100th order, and all that. So SL grating basically exploits that function of diffraction grating. And so here it is shown a high order SL spectrogram. Yeah. Which is basically, so what are the bright spots here? These corresponds to very specific lines of interest, and these lines can sometimes provide Doppler velocity precision less than a meter per second, and that's what is required. So what I'm showing here is a oscillogram taken from another spectrograph which is built in India at PRL Physical Research Laboratory in Ahmedabad. Now, these lines and this precision is required for certain applications, such as to get the precise age estimate of oldest star, because all stars have very fine structure, lots of lines, and you want to resolve them, and you want to get the line intensities. And so this is what you call the galactic archaeology. Okay, you want to know how old the stars are, and this is also used to search for planets around other stars. Okay, so there are planets. So if you have a planet, it basically wobbles the sun or whatever the parent star around them, and that wobbling is very small, of the order of a few centimeter per second or meter per second. Okay, that velocity with which wobble, and that's why you want to detect them. So this is a very a useful application of very high resolution spectrograph to detect planets around stars. Now I will go to X-ray spectroscopy. This is another domain where spectroscopy is very useful. These X-rays are high energy particles, as you know, and you encounter them in medical sciences more often, in your daily life than in any other applications, because they are harmful. But there are natural sources, the celestial sources, which emit X-rays, and we also do the X-ray spectroscopy. Now, X-rays detectors are there, which are photomultiplier tubes, but as well as the CCTs, which are charge-coupled devices, because charge-coupled devices are sensitive to X-rays also in an energy range between 0.5 kiloelectron volt to 10 kiloelectron volt. And we can, so what is the thing about X-ray CCTs is that number of electron hole pairs generated by high energy particles is proportional to incident X-ray photon energy here. X-ray CCTs therefore can work as a spectrometer also, if you can count electrons generated by them. So what it means here is that if you get there is some certain relation, so basically the work function is there. So if you have energy imparting on that as twice of the work function, you basically can generate 2 electron hole pairs, and so you know what energy the X-ray had. So X-ray work partly as a spectrometer, but of course they work only if you have a single photon event. So if a single photon falls, then you measure how many electron hole pairs it generated, and that you can use to calculate the energy of the incident photon. So for such events, yes, X-rays can work as a spectrometer, but for most other applications, we don't use X-ray CCDs as a spectrometer, but we use them as a high spatial resolution X-ray detector. To realize spectrometers in X-ray domain, we of course have to use a very fundamental thing about the X-rays, which is the Bragg diffraction. Okay, and that we have been seeing, which was flown in one of the observatory, the Einstein X-ray observatory. Now remember that to do X-ray spectroscopy, unlike what you do in radio, radio can be done from Earth, optical can also be done from Earth. X-ray spectroscopy or X-ray astronomy cannot be done from Earth because the atmosphere absorbs all the X-rays, so you have to go to the space. So all X-ray telescopes are flown into space, and the technique is very simple here. For a Bragg spectrometer, you have this Bragg crystal, and that Bragg crystal basically can be rotated to direct the diffracted beam towards the detector at a particular energy. So as you slew the crystal, you basically get an energy resolution falling on the detector. And so that's how you can get the spectrum of the X-ray. Now, this is one way to do that. But more advanced ways are now done in the modern telescope, which have been flown in past decade or so. And one of that is used in the Chandra X-ray telescope. Chandra X-ray telescope is named after a famous astronomer, Subrahmanyam Chandrasekhar. So here you use the gratings. Now gratings are very similar to what you encounter in optical, but of course now the spacing has to be finer, and the techniques are special. You have to use special materials. So in the case of X-ray, we use the gold wires, very fine gold wires are mesh or bars, with the spacing in the range 0.2 to 1 micrometer. So X-ray has got a very different technique of the X-ray mirrors, X-ray gratings and all that. But remember, the principle behind that is very similar to what we have already seen in case of optical. So such gratings can provide you high spectral resolution of the order of 1000 or so, in very high sensitivity, because these gratings are highly transmittive. CCDs can be used as a detector, in fact, to get a very high spatial resolution. And in fact, the Chandra telescope has the highest spatial resolution in X-ray telescope, which has been flown in past decade or so. You can also employ, instead of the transmission grating, the deflection grating in a very similar way we do in case of optical. And for example, here, if you remember, this is like in a grating formation, the roll-end circle. So you place it on roll-end circle. The X-ray mirrors sort of bring the focus the light here, and then you get diffraction. So what it is showing here the grating, and here is showing the detectors distributed on that circle, and you can form this spectrum. Such a technique was used in XMM Newton X-ray telescope. And now remember, these all gratings work at grazing incidence, which means that the angle of incidence is kept very small. They fall very parallel to the grating surfaces. And one can get a resolution in this particular case is about 6 milliangstrom at a wavelength of 15 angstrom or so. It's okay. So resolution of about 2,000, about 1,000 you can get in these cases. Now, this was just a very simple, in a very basic way, representing jumping from one domain to another in a quick fashion. So the X-ray astronomy basically enables us to do spectroscopy for elements which are there at very high temperature, very high energy particle in extreme physical conditions, which you see around black holes, for example. And so a lot of black hole physics is done using X-ray astronomy, and the X-ray spectroscopy, which enables you to detect highly ionized species in oxygen, iron, neon, magnesium. So these are all higher, atomic number elements which diffract the X-rays, or they produce, the X-ray lines very easily. So this information is very crucial to derive such extreme temperatures around these energetic, sources of the, something like black hole physics and all that. So I will summarize my talk here. Is that what we have seen in these slides, in this talk, is that we use different techniques to achieve the spectrum in the modern astrophysics, modern astronomy. So such as Fourier Transform is used in radio astronomy. Various kinds of diffraction gratings are used in optical and X-ray astronomy. Now, spectroscopy of celestial objects helps in detecting various elements in space. They also help in assessing density and temperature, and also the molecules, detection of those molecules which are responsible for formation of stars, as well as some link to the formation of life. Okay. Then the Doppler shift is a very important application of spectroscopy because that enables us to obtain velocities and in turn the distances to these objects. They also enable us to assess the kinematics and dynamics of objects and also to detect planets around stars. One thing you might have realized in this talk is that when you do spectroscopy, you basically disperse the light, and so you need large area telescopes. Because to start with, if you had a very few photons, you cannot disperse them, and so you need large telescopes to do spectroscopy, and that is why there is a quest now. There is a urgent need for having larger and larger telescope because we want to detect fainter and fainter sources or distant sources, very distant sources when the galaxies were formed and all that. And for instance, the 3.6 meter Devasthal telescope, although it's largest in India but not largest in the global context, there are telescopes like 10-meter telescope already working, which do more efficiently in spectroscopy than a 1-meter telescope. But despite that, now since we have a 3.6 meter, which is a very good aperture, actually very good collecting area for doing spectroscopy, and so the Devasthal optical telescope is suitable for many applications in the medium and high resolution spectroscopy. In fact, in future, the plans are to go for another large consortium of making a 30-meter telescope, which I'm sure you will hear after some time in another presentation. And so this is basically the end of the talk, saying that the spectroscopy drives the modern astrophysics. You cannot do much of the science if you do not have a spectroscopy. And spectroscopy, and to do that, you need larger and larger telescope, and that's why astronomers in every country are looking for to go for larger and larger telescope, and that's how we advance in understanding about the celestial objects. Okay, thank you. Questions. So there are two questions here in front of me. So the first question is that, is there any correlation between photometry and spectroscopy? If both are entirely different method of astronomical observation, which method is more convenient and reliable? Does radio telescope use photometry? Okay, so when you say photometry is basically counting the photons. Okay, photon counting happens everywhere. Either you do a single color or multiple color. So spectroscopy is also a photometry. That's measuring the photons. So I guess what you want to know is the imaging in spectroscopy. So imaging, as I said, that it's basically a form of, for example, a broadband imaging. Suppose I say there is a red color image, there is a blue color image, or there is a green color image. This is a very crude way of doing spectroscopy. Okay. So as I said, the photometry is a very general sense. It's a counting photons, which is there everywhere. And your second question is that radio telescope use photometry. I think it's very clear that every telescope counts photon. So every telescope does photometry. Okay. And the second question here is why there are dispersion axes bending for higher order in SL spectrograph images. Is there any remedy to it? Okay. The thing is that when you are forming these higher orders, there is a optics as well as the way these higher orders are formed. You basically cannot avoid these bending. So they are not formed in a straight line. There is a curved spectrum. I don't think there is any quick remedy for that unless you design a very complex spectrograph, multi-element. But once you do that, you lose light. So it's not very advisable to do that because this curvature you can solve basically when you do the data processing. So I do not see that this is any disadvantage except that you have to do more processing. Okay. Yeah, so there is a note here. It says that if someone misses today's live lecture, they can find it on ARIES Facebook page, of course, and also they will put it on ARIES YouTube channel. The links to these sites is available on ARIES official site, and I guess they are referring to the aries.res.in as well as on the Facebook official Facebook page of ARIES. Yes, you can also submit your questions later and also provide your feedback by using the link available below the videos. Thank you.